Hello everyone, welcome to Yourpedia education. So today we are going to discuss the questions from the digital electronics that are important for again BEL exam, right? BEL exam is on 31st of May, so mostly you have around 15 days are left, 15 to 16 days are left, right? So today we are going to discuss some questions that are from the digital electronics, and these are the really important questions, right? If I'm talking about digital electronics, in the complete exam you will find around 4 to 5 questions, and digital electronics is a easy subject, right? You can easily score around 5 out of 5, you can say like that, right? So which type of question he may ask you, I will discussing some of them, right? So to get this video, please join the link given below, right? Okay, let's start. The first question is BCD code for the decimal number 15. Whenever he is asking about the BCD number, remember that thing. BCD number means what? Binary coded decimal. Sometimes he may ask you the definition. What is a BCD number? So whenever you are writing a BCD number for a given number, let us take it is given to you that we have to write a BCD number for 15, right? So how we can write a BCD number for 15? So first what you have to do binary coded decimal. So 1 and 5, right? You have to write 1 and 5 separately. So what is the binary equivalent of 1? You have to write a binary equivalent for this one, and you have to write a binary equivalent of this 5 separately, right? You have to write the binary equivalent of this one and binary equivalent of this 5 separately, and each equivalent should be 4-bit. Remember that thing, each equivalent should be 4-bit. Let us take, I am writing this 5 in the binary. How we can write the 5 in the binary? 1 0 1. So this is a 3-bit number. You have to convert this number into 4 bits, so you have to increase the number of zeros. You can put the 0 on the MSB side. So how we can write the 5 in 5 bit? That is 0 1 0 1. Okay, next is 1. How we can write for 1? That is 0 0 0 and then 1. So basically this is the number for 15, that is binary coded decimal, right? That is the number 15, that is for binary coded decimal, right? So now you understood how we can write a binary coded decimal number for a given number. What you can do, just write the binary equivalent for each digit and write a binary equivalent of 4-bit for each digit, so you will get a BCD number from there, right? Next question, you have a octal number. This is your octal number because its base is 8. You have to find its equivalent. What? Binary equivalent, decimal equivalent, or base 16 equivalent. So first convert this, because the first one is what? That is a binary decimal equivalent. So convert this one. How we can convert a octal or any base? Remember that thing, any base to decimal. How you can go that? Let us take it is a 454. So how we convert that? First, if you convert any base to decimal, your LSB must be multiplied by base to the power 0. So here is the base is 8. So I am putting that one 8 to the power 0. Then plus your next bit, that is 5. It should be multiplied by base to the power 1, right? Whenever you are converting from any base to the decimal, you have to follow this step. Plus next bit, that is MSB here 4, it should be multiplied base to the power of 2, right? So when you solve it, that is become how much? The 4 times 64 plus 5 times 8 and plus 4 times 1. So 4 times 64 is 256, and 8 times 5 is 40, and 4 times 1 is 4, so that is going to be 300. So our answer is 1. You can go for the second answer if you are trying to find octal octal to the binary. So what you have to do, first write a 4 bit, this is octal, write a 3 bit number equal to the 3 bit number into the binary, that is 0 1 0 0. Next is 5. So 5 can be written as 101. Sorry, you are writing we are writing 3 bit, not 4 bit, so that should be 100, and that 101, and that is 4 again, 100. So what will be the answer? That is 100 101 100. That is your binary equivalent. And if you want to convert this octal number to the hexadecimal, the easiest way, first convert it into binary, then make a group of 4 like this, and like this. So you can check that MSB is going to be A, right? Oh sorry, not A, that is 1, because it is 1. The next one is 10, that is represented by 2, and the last one is 110, that is 8 plus 4, that is 12. 12 can be written as C. So the hexadecimal equivalent is 12C, like that. So basically what will be the answer? Answer will be A. The access 3 code of a decimal number 15. So whenever you are writing access 3 code of a given number, so access 3 code is BCD plus 3, right? I'm writing access 3 code of 15. So first I have to convert this 15 into BCD number, right? BCD number is what he did. That should be not like this. This is 0001, right? And then I think, okay, that is the final answer, sorry. So first you have to write the binary number for 1, that is 0001, and then you have to write the binary number for 5, right? That is 001, and right, and individually add the 3 in each digits, right? Okay. So basically if you have the number is 1, so you are first write the BCD number for this one, that is 00001, and 50101. Then you have to individually add the 3. Access 3 code means you have to add 3 in each digit, right? That is 0011. And when you add them, 1 plus 1 is going to be 0. Then 1 carry here, 1 plus 1 is going to be 0, 1 carry here, to 100, 0100, right? Next one is what? That is, then 1 plus 1 is 0, 1 carry, 1 plus 1 is 0, 1 carry, 1 plus 1 is 0, 1 carry. So this is, so if I write the access 3 code for 15, that is going to be 1001 4 times 0. So this is the access 3 code. So always remember, whenever you are writing access 3 code, you are writing access 3 code for a given number. So first convert that number into BCD, then add 3 in each digit, right? Remember that one, and you will got the access 3 code for that one. Okay, which of the following is our self complementary code, right? So basically 2421, 8421 and the access 3 are the example of self complementary code. See, basically if you have a weighted code, like this, these are called as weighted code. If you have a weighted code, inside the weighted code, basically if the sum of all the weight, if sum of such code having property that 9's complement of a decimal is obtained by adding 1 and 0 into that one, right? If the weight of the each code is going to be 9, that will be self complementary code, right? So basically 8421 are the self complementary code, 8421 access 3 code, 2421 are the self complementary code, right? 8421, 2421, right? Access 3 code are self complementary code. Self complementary code is what? That have 9 complement of a decimal number is obtained by directly changing 0110, right? That code are called as self complementary code. 2's complement representation of -9. What does 2's complement representation of -9? First represents the 9, that is 1001. Then you have to take 2's complement because it is a negative number. So whenever you are writing a number in 2's complement format, remember the positive number is written as it is And in negative numbers, what should you do? First write the positive equivalent of that number, then take its 2's complement. How we can take the 2's complement? First write the same number, then in positive, then take its 1's complement, and when you are taking its 1's complement, change the 0 to 1, 1 to 0. So this is your 1's complement, then add the 1 in the LSB. So that is going to be 1, 1, 1 and 0. So this is your what? The 2's complement equal representation of -9. So that what will be the answer? The answer will be C. Okay, he is asking for 2's complement, right? How many bits are there? It is using the 5-bit representation. I am using there is 4-bit representation, right? I am adding 1, that is 1. Yes, 1, 1, 0, and then you have to put a 1 here, right? To make it 2's complement form, right? The greatest negative number which can be stored in a computer that has 8-bit word length and use 2's complement arithmetic. So whenever we are going for 2's complement arithmetic, the numbers range is minus 2 raised to power n minus 1 to plus 2 raised to power n minus 1. These are the range of numbers, right? Whenever you goes for 2's complement representation, then he is asking that what is the greatest negative number? So negative number is minus 2 raised to power n minus 1, and in place of n you can replace 8. So minus 2 raised to power 7. So whenever you go for 2 raised to power 7, that is 128. So it's going to be minus 128, negative number. Answer will be C. Given that the decimal number minus 19 and 8-bit 2's complement representation is given by, okay, minus 19 2's complement representation is given by what? So what should we do? We have to use the 8-bit representation for that one. So first you have to write the plus 19. The plus 19 can be written as what? How you can do that? If you don't know directly, then you can do like this. Divide that by 2, that is going to be 9, and you will left with 1, 2. When you divide this 9 by 2, then you will left with 4, 1 remainder. Then you have to divide by 2, you will left with 2, remainder is 0. When you divide by 2, you will left with 1, you have 0. Write it above. So you will got a number that is 10011. So the note 2 into plus 19 can be written as what? That is 10010. Oh sorry, 1. This is your 19. Now you have to take its 2's complement, but remember he says 8-bit. This is having only 5-bit. So increase the number of bit, add the zeros, 1, 2, 3 and 4 zeros I have to add here. Not 4, 3 zeros, right? It is a 5-bit number. 3 zeros are there, then 1, 0, 0, then 1, 1. Now after getting this, what you have to do? You have to take its 1's complement, then it is become 1, 1, 1, and it is become 0, then 1, 1, 1, and then 0, 0. Then you have to add the 1 in the LSB. So that is the minus 19 equivalent in 2's complement form. That is going to be 1, 0, 1, 1, 0, 1, 1, 1. Right. So this is 2's complement form of minus 19. So answer will be B. So like that. So in the previous case he is asking, in that case he is asking for the 5-bit representation. That's why I put a extra one there, right? So that means if you directly do it here, so first you have to replace a 0, that will become 1 here, and that one will be represented like this, right? Okay, next one. A 3-digit decimal number requires for representation in a conventional BCD format. See, if you have a 3-digit decimal number, each digit of a decimal number can be represented by 4-bit of a BCD binary number to write a BCD. So 4, 4 and 4. So total is how much? That will be 12. So 4-bit for first number, 4-bit for second place, right? There should be 4-bit for first place, there is 4 bits, 4 bits, 4 bits. So there are total 12 bits we are required, right? 12 bits. Answer will be C. Compute the Hamming distance between two valid codes. These are the two valid codes. So whenever you are calculating the Hamming distance between two codes, you have to do the XOR of these two codes, right? Whenever you do the XOR of these two codes, that XOR of same number is 0. When you calculate the XOR, right, you calculate the XOR of two numbers. Oh sorry, that is 0 0 0 1 0, right? So basically when you calculate the XOR of two number, when the two numbers are same, then XOR is 0. When two numbers are different, then XOR is 1. So these two numbers are different, then XOR is 1. Two same, 0, same 0, same 0, same 0, then two numbers are different, that is 1. And count the number of 1 inside that one. There are two number of 1s are there inside this one, so that means its Hamming distance is 2. Or directly you can check the how many bits are different from the in between these two. So first bit is different and the last bit is different, rest of the bits are same. Or directly you can calculate the Hamming distance. Hamming distance means the two codes are different in how many bits, that is called as Hamming distance. Next is, in a single error correcting Hamming code, the number of messaging bit in a block is 26. The number of check bits are in the block would be. So whenever you are calculating the check bits, so first thing what you have to do, first is number of bits are 26, the number of bits are 2 to the power n minus 1 plus 1, that is equal to 26. When you replace this equation 26, then you have to use your options. When I put 3 here, 3 here, the 2 raised to power 3 is going to be how much? 8 minus 4, that is 4. That option is not correct. When you put 4 here, so 4 minus 4, 2 raised to power 4 is 16. 16 minus 5 is going to be 11. When you put 5, 32. 32 minus 6 is going to be 26. So which option is correct? That is 5. You can directly use this equation. The number of bits always equals to 2 raised to power n minus n plus 1 whenever you are using Hamming code for a message block and for you can say the error correcting and correction, right? Binary 0 and 1 corresponding to what? Binary 1 and 0, provided that different stages are DC levels, right? These are the DC level. It provides the information about switching condition of the circuit, right? So these are the two different DC levels. So basically sometime the 0 will be represented by 0 volt, right, and 1 will be represented by 5 volt, or in some of coding we will represent 0 as a 1 volt and 0 as a minus 5 volt and 1 as a 5 volt. So there are two different DC level to represent. We use two different DC level to represent, right, either 0 or 1. So answer will be C. One hexadecimal digit in some time refers to as. So whenever we are taking the hexadecimal digit, each hexadecimal digit represents the nibble, right, nibble. So basically that represents the nibble. One hexadecimal digit sometime represents the nibbles, right? What does will perform the conversion of a 4-bit BCD code to 7-segment display required to drive the LED, that is a decoder. We use that decoder name is decoder BCD to decimal converter. That recorder is given the name as BCD to decimal converter, right? The best representation of a negative number is, that is 2's complement form. See, inside there are limitation of the rest form, that is there are sign magnitude representation, 1's complement representation and 2's complement representation. These two, sign magnitude representation and 1's complement representation, has their limits. What is that limits? The limit is that there are two representation for 0, that is plus 0 and minus 0. That's why they will not have that much practical importance. Inside the computer, whenever you are performing anything, that will be done using 2's complement form. So the most widely used is 2's complement form to represent the the negative numbers, right? By taking 2's complement again of 2's complement of a binary number, we will get the original number back. When you take the 2's complement 2 times, you will get the original number. BCD code is error correcting code, error detecting code, both A and C, none of these. See, BCD is just a binary coded decimal number. It is not any type of error correcting and detecting code. Booth algorithm is associated with, the Booth algorithm is associated with binary integer multiplication. See, remember these things. Don't think that these are out of syllabus, right? You should know these things, right? When binary adder is add as a BCD adder, the sum is see, if you are adding two binary numbers to a binary numbers, if you are adding by using a BCD addition, in BCD addition we can only represent from 0 to 9. We can't represent 10, 11, 12, 13, 14. If you want to represent 10, 11, 12, 13, 14, then you have to add 6 in the result. So if you want directly, if you are adding two numbers, and if you want a correct result, the result should be less than 9. If it is greater than 9, then you have to add a plus 6 on that one, right? So answer will be A. Which of the following is self complementary code, right? The access3 code is a self complementary code. Okay, the minimum decimal equivalent of a binary number. See, yeah, this is an important question. We have to find its minimum decimal equivalent. Try to understand the concept here. If you are trying to find its binary decimal equivalent, so first what you have to do, you have to check how much is the maximum base we can have with this number. See, there is C. A is represented by 10, B is represented by 11, so C can be represented by 12. So the maximum base for this number can be 13. Remember that. Oh sorry, minimum base can be 13. Above that one, any base is fine. You can't take 12 base because you have to find the minimum decimal equivalent. So you have to choose the minimum base, because if you are representing, you are going for a binary number. From binary number you can represent only two numbers, 0 and 1. So with binary base we can represent two number. If you have a octal base, you represent 8 number from 0 to 7. Similarly, if I choose the 13 base here, I can represent a number from 0 to 12. So if you want the minimum decimal equivalent for this one, you have to choose the base as 13, and then you have to represent 12 into 13 to the power 0, then 1 into 13, then plus 1 into 13 to the power 2, and then add them together, you will get 194. The answer will be B. So these are the tricky questions. So these are very important for a BEL exam. So basically the last question is, when signed number are used in binary arithmetics, then which of the following notation would be unique representation for 0? I already discussed this thing. Sign magnitude representation, 1's complement representation, 9's complement representation are not used. 9 is not used in your communication or not computer, because it is not a binary arithmetics. 9 complement. 9 complement will be taken for the when you have a decimal number. Now he is asking for the binary arithmetics. In binary arithmetics, sign magnitude has 2 representation for 0, 1's complement also have 2's representation, only 2's complement have 1 representation for binary 0. So there are more questions for this slide, so let's stop here. So hopefully this information and these questions will help you. These are really important questions for your BEL exam, right? Go through that one, right? These are really important, I'm again saying, and rest of the question we will provide in the paid module, right? So if you are preparing for this one, you may join Yourpedia, because you have only around 14 to 15 days left. So if you want to crack this exam, you have to try to solve as much as question as possible, right? For that one, we already launched a module that is only based on problem solving, or that is only we will provide you the concept through questions, right? We will provide you the video of 1000 questions and around 3000 questions for your practice, right? Including the test series also there. So if you want, you can join Yourpedia. Thank you.